we are going to start with a talk by Pradeep Rakikumar. It's a great pleasure to have him here. He's an associate professor at CMU. And he's going to tell us what PPDSparse stands for.
Sounds good. Thanks to the organizers for inviting me to be here. Today I'm going to talk about PPDSparse, which stands for Parallel and Primal-Dual Sparse method for extreme classification. So I'm going to focus more on the intuitions that both we motivated us even before we got into this, and also that underlies this line of work. I'll also motivate or give the motivations for PDSparse, which is a precursor to this. So extreme classification, we have all seen examples so far, and we will continue to see more examples. But so this is more of setting up the notation for the setting of extreme classification. So I have capital K classes, where K is 10 to the 6 or potentially higher. 10 to the 4, 10 to the 5 is common as well. And then my data has D, capital D features, which could also be of the order of 10 to the 6. Okay, so a high dimensional setting, and which is not uncommon, especially if you do one-hot encoding of a whole bunch of categorical features. And then you have capital N samples, where N again is of the order of 10 to the 6 or 10 to the 7. These are pretty common numbers, right, or potentially even larger. Now, with these three key parameters, capital K classes, capital D features, capital N samples, even if I use linear models, the number of parameters scales as order D times K, which is very large. Even just linear models, right? And so if I have a multi-layer perceptron, then you can essentially think of it as multiple linear models whose parameters you have to instantiate. And then I can also think about, you would then say, okay, so the primal problem has a lot of parameters, so why not look at the dual? And if you look at the dual, that also has a large number of parameters. Typically, for instance, for linear models, the duals would have order N times K, which is also large. Okay? And so the number of dual variables would scale with the number of samples times the number of classes. And so this is also going to be large. And so just to give you a sense of the complexity of this, even with a linear model, computing a single gradient is very expensive, right? So if I'm doing an optimization of some primal objective, then it's at least order D times K, and that's for a single iteration. Very expensive. It might not even load into memory, right? So there's also space complexity, memory as well as computational complexity. And so this is really the setting. And until Manik's work, I mean, so this was like, this seemed almost impossible to even think about starting to actually do some rigorous work in this space. But I also wanted to mention a statistical caveat, which some of the papers might not talk too much about, but this is really the setting of high dimensional estimation. So if in such so what do we call as high dimensional models, where the number of model parameters is very large, typically even larger than the number of samples. And so in this setting, we know that statistically consistent estimation is not possible. So let's just imagine that I give you lots of computational resources, access to huge clusters, and you manage to fit your classifier. One thing you need to worry about is not just whether your training error is low, but whether this classifier is generalizable. So on unseen test data, whether this classifier will perform well. And so for this, if you are in a very high dimensional context, you are out of luck, in general. And so what people have now realized over the last decade and a half is that you can get consistent estimation. So this is just putting on the statistical guarantee hat, right? So I'm just focused on statistical guarantees. It is possible, provided we impose some structure on the model parameters. And so what do I mean by structure? And so now we have a very good language for expressing such structure, ranging from sparsity, group sparsity, structured sparsity, low-rank structure, among others. So the question really that we need to ask, at least for statistical reasons, but also for computational reasons, what kinds of structure can I impose on extreme classification models? So that's really the key question that motivated us. And so let me set up some more notation so that we can talk about this question in more formal terms. So I have a classifier f that goes from R to the D, since I have D features, to 0, 1 to the K. So we are in the general setting of multi-label classification, where I could output K bits. Right? So the bit will be 0 if that label is not present, 1 if it is. So in the multi-class classification, this bit vector will only have a single 1. Okay? So just for the class that you're predicting, everything else will be 0. But in the general multi-class classification, this could be a general bit vector. Okay? So that's my classifier, R to the D to 0, 1 to the K. And so typically in machine learning, we parameterize or we work with score functions, where here I'm going to denote that by H, which goes from R to the D to Euclidean space. So even for binary classification, so when I'm training a classifier, my goal is to take the inputs to a bit, 0 or 1. So, but typically what I do is I map the inputs to the real line and then threshold it to get my bit. Right? So this is a typical way in which I train classifiers. Even in this multi-label setting, or multi-class classification setting, I can also map the input to a k-dimensional Euclidean space. And then I can go from this k-dimensional Euclidean space to k bits. Okay, so one way I could do that is to take these, so this function h is a vector valued function. So think of it as actually k different functions, h1 through hk, h capital K. And so my classifier f would just be thresholding each of these capital K functions. Okay, so if it is greater than 0, I will mark that bit as a 1. If it is less than 0, I'll mark it as a 0. Okay? And so this is my classifier, and this is my score function. And the advantage of a score function is that once you map it to a Euclidean space, it's easy to think about parameters, and it's easy to compute gradients and all those other things. Okay? And so the running example is going to be for a linear classifier, where the score function h of x is going to be some matrix w times x. Okay? And remember that x here is my input, which is d-dimensional. And so this w is going to be a k times d matrix. Okay? So that w times x would be k-dimensional, because I want my score vector to be k-dimensional. Okay? So you can think of the output of h of x as how much I think that each class is present, going to be present for this particular input. And so even though I'm going to be talking about linear classifiers, most of the motivations in this line of work can extend to more general classification functions and score functions. Okay, so I have this linear function, h of x, which is w times x. And so now let me start thinking about the number of model parameters and what structure I can impose. Right? So if I look at the number of model parameters, it's k times d, because this w is really my parameterizes my linear score function. Right? And so I can say, okay, these are too many parameters, so I'm going to impose some structure. A common structure is that of sparsity, but I'll say that this w, capital W, has to be sparse. Now, the issue is that computational scalability might require a very, very high level of sparsity, which may not be a natural assumption. You may say, okay, W should be reasonably sparse, but I can't imagine that W is extremely sparse, right? Constant number of zeros, or constant number of zeros per row or column, and so on. So these are extremely sparse matrices. I can always assume that, but then you may push back and say, is that actually reasonable for the problem, right? It doesn't seem very natural to assume that. What's more, it doesn't really give you as much benefits as you might imagine, because gradient computation, you're still going to be hit by order k times d. Okay? And so this is still an issue. And so you're going to be, this is going to be a problem even with stochastic gradient, right? I haven't really talked about the complexity with respect to n even, right? Just a single gradient for a single sample is going to take order k times d. Expensive, right? And so what people have done is try to search for other more reasonable structures. A common thread of work is assuming low-rank structure. And you can assume this low-rank structure in various parts of the story. So one particular structure can be that this W has to be low rank. And so that's a reasonable structure. You can also assume that the labels are embedded in some lower dimensional subspace. That is also a reasonable assumption, right? Because if I have 10 million 10 million labels, you think that, okay, maybe this is too many labels. There are ground truth kind of semantic labels could be fewer potentially. So maybe if I can just embed these 10 million labels into a lower dimensional subspace, things would be great, right? But the question is, how are you going to get that embedding? So the typical way it's done is you compute a linear embedding, and that has issues. It has what could be called the Platypus problem, which is what Charles Elkin mentioned to me. Okay, so what is the Platypus problem? So this is a platypus, which we may all have looked at in our high school biology class. So the platypus is a weird animal. It's an egg-laying mammal, right? So initially when scientists came across this, they thought it was a hoax because it has all these weird features. But the interesting thing is that it is still a bona fide animal. And so imagine that I want to predict animal categories, right? And so the issue is that since this is a relatively rare animal category, the labels of the platypus as well as associated features could be sparse. And so if I'm going to think about some embedding of all my labels, I might potentially miss this particular label, the platypus, right? Because I may focus on the mammals that typically don't lay eggs, I may focus on birds that do lay eggs, and then I may miss this intersection. But the interesting thing about the platypus is that it's very, very distinctive, right? From its duck beak to certain various other features. So if I give you the features of the platypus, it's a very, very easy prediction problem. So essentially with this embedding, you are missing out on what should ideally be a very simple prediction problem. And so this can happen whenever you have a long tail, where even though it's a long tail, these are actually simple prediction problems. But because of the various embeddings and other things that we do, we might actually miss out on what was actually a very easy prediction problem. And so this is really what I call the platypus problem. So how do you address this? And so maybe instead of label embeddings, I could do something else. So another popular line of work by Prabhu and Manik, Choromanska, Langford, and others, is to, and even David Sontag talked about it in the morning, is that I might have a tree-structured partition of the labels. And so this has both computational advantages as well as potentially statistical advantages. But the issue is that to find the optimal tree, and in fact the topic today morning was also about how do you learn the tree, how do you construct the tree, is computationally challenging if I want optimality. And so there are various heuristics that I can use to compute the trees. But again, what are the guarantees? Right? So it'll be difficult for me to give generalization error bounds if with many of these heuristics, though it's a very reasonable approach. And so that's really the setting. So this is how we are looking at things, right? So what kind of structure? Sparsity might be too stringent, or rather I might need a lot of sparsity. Low rank structure or embedding has issues, the platypus problem. I could look at trees, but where do I get the trees, and so on. Okay? So the question really is, can I impose some other much, much more natural structure that all of us here would agree, oh, it's very reasonable. I cannot imagine this structure not holding, right? I want you to have that feeling, saying that, okay, this is extremely reasonable. So let me set up some notation before that. So L, capital L, is going to be a loss function. Okay, so it's going to take first argument is going to be the score vector, which remember is k real values, and its second argument, so it's a k-dimensional real valued vector, and the second argument is a k-dimensional bit vector, right? And so I have this loss function. So what it tells me is that, so the first argument, let's say the score vector is z. It tells me, and if the label vector is y, it tells me how good is the score vector, how well does it match the true, ground truth label vector y. Okay, so this is my loss. So we want to work in this general setting for general losses. So here is some additional piece of notation, which is this: given a sample xi, yi, I want to talk about the set of positive labels, which I'm going to call C plus I. Okay? It's the set of positive labels which is out of the k possible labels, look where yij is actually equal to 1. Look at this k-dimensional bit vector, see which coordinates are actually 1, right? So those are the positive labels. Look at which coordinates are 0, those are the negative labels. I'm going to call that c minus I. Okay, so the subscript I is because it's the sample I. Okay, so this is my a very important piece of notation. The set of positive labels given sample I, the set of negative labels given sample I. And so now let's talk about some natural assumptions, right? So I put it in quotes because it's natural to me, but I hope you would also agree that these are natural assumptions. So here is one such assumption. For any sample, the set of most confusing labels is sparse, which are called MCL sparsity. So what does this mean? Let's unpack that a little bit. So for sample xi, yi, what is the set of most confusing labels? You look at the negative label, c minus I, and you look at which of these negative labels attain the highest score values. Okay, does that make sense? So I have the set of negative labels for sample I, and then you look at which of these take the exact highest value of the score function h, right? Where hj of xi is the largest. Okay, so this is my set of most confusing labels. Why do I call it most confusing? Because I want my score function to be large for the positive labels, right? So wherever these score function values are large, I think of them as positive, right? And so if I think of the score function as what I have learned, for this sample I, it's most confused at those coordinates, negative label coordinates, where it also attains high values. Does this make sense? Right? And so in general, if our score functions are reasonable, it's typically only going to be high at a few label coordinates. Okay? So typically it's going to be small. In most places, it's essentially going to think that the label is on at only a few coordinates, if your score function is good. But I'm not even assuming that. I'm just assuming that the most confusing labels, the set of most confusing labels is sparse. Okay? So in other words, it's not the case that for all the negative labels, it attains an equal and high value, right? So I'm not going to assume that. Okay? So in other words, if you think in terms of this optimization problem that I have here, I'm going to assume, not assume that it's attained at a unique label, but the set of labels at which it attains this maximum is small. So this seems reasonable, right, for a good score function. And so that's my assumption, MCL sparsity, most confusing label sparsity, okay, which I hope you would agree seems like a reasonable assumption. But assuming it's a reasonable assumption, how do we then enforce this assumption, right? So primal sparsity was easy to enforce. If I have a matrix W, I think this matrix W is sparse, I know how to enforce the sparsity, right? You put L1 regularization or some sparsity encouraging regularization, and then I'm done. But how could I possibly enforce MCL sparsity? It turns out that this is an easier problem than you might suspect, and some of you might have already suspected how to enforce that sparsity, because this is naturally associated with a margin-based loss function, which is given here. So L of z comma y is essentially the cost that we associate with the score vector z given label vector y is how much the negative labels have a higher score than the positive labels, right? So the only way for my score vector to get a cost of 0 is for the positive labels, the minimum score for a positive label to be a margin above the maximum score for a negative label. Okay, so that's what this this loss says, and it's a very natural loss in multi-label classification settings. Okay, so why is it associated with this loss function? So what we show in 2016 in the PDSPARSE paper was that if you use this margin loss, then MCL sparsity, the most confusing label sparsity, that assumption entails sparsity of dual variables. Okay, and what's more, for covariates in general position, this also entails primal sparsity. So in other words, this MCL sparsity assumption entails both primal and dual sparsity if you use the margin-based loss function. Okay, so so you definitely get sparsity of the dual variables, but the covariates have to be in general position. What does that mean? Well, if the covariates are drawn from a continuous distribution, then they will be in general position with very high probability. Okay, so I'm not really assuming anything about the distribution. So long as it's a continuous distribution, they will be in general position with high probability. So it's a very mild assumption. Under that assumption, you also get primal sparsity. Okay, so both your dual as well as your primal variables are going to be sparse automatically, right? I'm not starting off by assuming that the primal and dual variables are sparse. I'm only assuming MCL sparsity, but we have a theorem that shows that MCL sparsity in turn implies a very high level of primal and dual sparsity. Okay, and so what we did was then we developed an algorithm that simultaneously leverages the primal and dual sparsity so that it can compute gradients efficiently and it can compute the optimum efficiently. So it's essentially based on a very scalable variant of constrained greedy coordinate descent, right? In coordinate descent with constraints, so that's essentially the Frank-Wolf. It's what we essentially used was a fully corrective block coordinate Frank-Wolf. But if you throw out the constraints, what you would end up with is a constrained greedy coordinate, a greedy coordinate descent, where you pick coordinates one by one. Okay, and if you recall what I mentioned very early on, the gradient computation seems like a very expensive thing. But because the primal and dual variables are both sparse, I can compute and maintain the gradient very efficiently. I don't need to pay the full price. Okay? So you need both primal and dual sparsity for that. Just primal sparsity alone, it's not going to let you go free, or dual sparsity. So the overall computational complexity scales as order n times the number of non-zeros in the primal parameters plus d times the number of non-zeros in the dual parameters. So the computational complexity actually depends on both the primal and dual sparsity. So overall, this scales as n times d, which is essentially the input problem size, right? The x has this, our design matrix x has this size, n times d. And so this is our overall computational complexity. Okay, very scalable. And so this was our PDSparse. We call it because we explicitly leverage primal and dual sparse. But it's essentially the underlying idea is MCL sparsity, most confusing label sparsity. Right? So what are the caveats with this? The caveat is that especially in a case where I have, let's say, 1 million or 10 million labels, classes, I may want to parallelize, distribute my computation across multiple compute nodes, right? Or even over multiple cores. So the caveat is that the margin loss that we deal with is explicitly not decomposable. Right? So then one thing you could do is do a parameter server or some other such architecture to still decompose, or not decompose, but to still distribute my computation over a distributed compute infrastructure, but this is still expensive. Right? The issue is that this is not embarrassingly parallelizable. And what is embarrassingly parallelizable? Well, one versus all is embarrassingly parallelizable. Right? In one versus all for a multi-class or even multi-label, you try to predict a single label against all other labels. Right? And so you can do this, fit a model for this for all the 10 million labels independently. Right? So this is very parallelizable, and so this is really the key idea behind DISMEC. Right? Of course, they have some more, but the very recent DISMEC is essentially using this one versus all based loss. Now the issue with the margin based loss, which is connected to this MCL sparsity, is it's not decomposable. Right? And so the question we were asking is that, can we still use this one versus all loss and still have a natural sparsity assumption that's associated with it? Right? One question you may have is maybe it's actually associated with MCL sparsity as well. Unfortunately not. If you're going to use the one versus all loss, then it's not associated with MCL sparsity. What do I mean by that? If you assume MCL sparsity, it does not entail primal or dual sparsity given the one versus all loss. Okay, so again, just a piece of notation so that you're clear what I mean by the one versus all loss. So again, this is L of a function of score vector Z and label vector Y. It just decomposes over the classes K, and then it's just a hinge loss for your score for class K and the label for class K. Okay, so it's a very simple decomposable over the classes. And like I said, MCL sparsity, assuming MCL sparsity, does not entail anything about primal or dual sparsity. Okay, so most confusing label doesn't work, so you have the most confusing question, if you will, right? Which is there any other sparsity assumption I can make do, which is amenable to this loss? And why do I want this loss? Because this is very, very embarrassingly parallelizable, right, to actually work with. So let's look at, so instead of most confusing labels, let's look at another notion of that's drawn by the structure of this one versus all loss, which is the active labels per sample. So instead of the most confusing labels per sample, let's focus on the active labels per sample. So what is the active labels per sample? So for sample I, it's the set Ci, which is a set of all labels K such that the sample I will fall within the margin. So think of this Hk as a linear function, a hyperplane, right? And so it's the set of all labels such that for the hyperplane corresponding to that sample, this sample would have fallen within the margin, right? So algebraically, it's just yik times hk is less than or equal to 1. Okay? But geometrically, that's what it means. Like in an SVM, right? You have some samples that are going to fall within the two margin hyperplanes, right? And so here, because we have one versus all, you have a separate hyperplane for each class, right? And so for a given sample, you look at all the different hyperplanes where this sample would fall within that margin, right? And so you would then call it an active label for this sample, okay? And so you can then average the number of active labels across the samples, and so let's call that Ka, right? It's the average of all these CIs over the n samples. And so what you can show is that the dual sparsity with the one versus all loss entails that Ka is small. The average number of active labels is small, right? So in particular, I can assume that it's extremely smaller than K, possibly a constant, right? You may say, okay, this seems a little bit more confusing than the MCL sparsity, right? Because why should I imagine that the active labels per sample is small, right? So let me give you a slightly more intuitive, but slightly different assumption, which is based on support vectors, right? And so here, I'm going to focus on a single hyperplane, okay? Let's say the hyperplane for class K, and focus on all the samples that are going to fall within the margin, right? So these would be the support vectors in the non-realizable case, right? So again, these are going to be the set of all i's from 1 through n, such that yik times hk is less than or equal to 1, right? And so these are essentially the support vectors for the hyperplanes for the kth class, right? And so you can now compute the average number of support vectors, average sk over the capital K classes. And so you can also show that the dual sparsity with the one versus all loss entails that NA is small. The average number of support vectors is small. And so this is not surprising, right? So especially those of you who have worked with SVMs, this many people have shown. Okay? So this is not going to be surprising for you, right? So in the completely realizable case, there are going to be no points that are going to fall within the margin, right? So you're only going to have points that are going to fall on the margin hyperplane, and so typically that is extremely sparse, right? So that's an assumption. This NA is extremely smaller than n, but and then the previous assumption of the number of active labels also follows from this, because capital N times the average number of active labels is capital K times the average number of support vectors, right? Because both of these are just equal to the sum of all support vectors across all classes, right? And so the average number of active labels and the average number of support vectors are really just two sides of the same coin. So if one is small, the other will be small also, right? And you can also show that the dual sparsity would entail primal sparsity, similar to before. But there is one caveat, right? We are not in the clear. We cannot, in general, assume that the number of support vectors, that is samples within the margin, is constant, right? It may be a small fraction of the overall number of data points, but I cannot assume it's constant, right? So imagine I have 1 million data points. The number of data points that are going to fall within the margin are not going to be independent of the total number of data points. If I go from 1 million to 10 million, you're not going to assume that it's not going to scale the number of points that are going to fall within the margin, right? Typically, it's going to scale with capital N. It's not going to be a constant. It's not going to be 10, right? You may be lucky, and it could be 10, but it need not be, right? But Manik did point out in our discussion yesterday that it could be that in certain tail classes, you are essentially dealing with a realizable class. And so this again goes back to the Platypus example that I mentioned, which is that in the tail, you may actually have very simple problems. And so they may actually be realizable rather than non-realizable. And if they're realizable, then the number of support vectors could well be constant, right? But modulo that, in general, I cannot assume, right? And so this is not really a reasonable assumption. 0 minutes, okay. Maybe just 2 minutes since we started a bit late. And so instead of assuming that, I'm going to talk about the number of positive labels. Okay, so for sample I, these are going to be those bits which are 1, right? So I already defined this notation, and I'm going to talk about the average number of positive labels, right? And so this is much more natural to assume as constant. In typical applications, this is less than 10. In multi-class classification, this is 1. There is a single bit that's non-zero, right? So for all, this is arguably even more natural than the MCL sparsity, right? And so this is what I'm going to call NPL sparsity. And associated with it is also the number of positive samples, which is the other side of the coin, where for each sample I can talk about the number of classes for which the corresponding bit yik is 1, and talk about the average number of positive samples per class. And this NP would be very, very small. It would essentially scale as capital N over capital K. So in this case, the more the number of classes, you're better off, because KP is typically a constant. Think of it as 1 or 10. So NP, the average number of positive labels per class, is going to scale as capital N divided by capital K. So here you get the benefits of large number of K. Okay? So the upshot is that the reason I brought these up is that you can show that you do not have hard sparsity, but you have weak sparsity, which is that the optimal primal and dual parameters, their L1 norm is bounded by the average number of positive labels. Average number of positive samples per class. Okay, this NP. You can get an even finer result where the optimal primal parameters for class K, you can bound it by the number of positive samples for class K. So you can be even finer grained. And so the upshot is that the primal and dual parameters are weak sparse under the NPL sparsity assumption, which all of you would agree is very reasonable. And so if it's weak sparse, I can stochastically approximate it by a hard sparse thing, a vector, by just standard approaches such as weighted sampling that I'm not going to go into. Okay, and so that was really a parallel and primal dual sparse, where we assume this NPL sparsity, which entails weak primal and dual sparsity, and we developed an algorithm that again leverages both primal and dual sparsity with some more technical machinery involved in because we don't have hard sparsity, we have weak sparsity, so there were some stochastic approximations of our vectors that we actually had to do in each iteration, but it's embarrassingly parallelizable. Right? And so the complexity per class is the Kp squared divided by K. Okay, so here are some results. So since I don't have a lot of time, let's just look over the first row, and then I'll stop. And so the first row is Amazon and 670K. So here I have 500,000 training samples, and the K is 670K, 670,000 labels. And so here, PDSparse did not even load into memory. it ran out of memory because each compute node was not that, did not have a very large memory. And PPDSparse was not only ran out of memory, it was one of the fastest. Fast XML was faster than PPDSparse, but it gave, what we had was, so actually for training, we were much, much faster. For testing, fast XML was faster. But our accuracies were much, much better than any of these other methods. And so this is PPDSparse. So again, the same thing holds. Either we are state-of-the-art or close to the state-of-the-art. So let me just summarize. Extreme classification has both statistical and computational bottlenecks, which requires us to think and impose structure, right? And so the important question is, what is reasonable structure? Because you can always come up with structure and impose it. But the question we always need to ask, and that also came up in discussion with Manik, is that what is a structure that would be reasonable for our application that you have in mind, or in broad, across broad applications? And so what we found were some very natural assumptions, which we call MCL sparsity, or most confusing label sparsity, and number of positive labels, NPL sparsity, which result in either hard or weak primal and dual sparsity, which you can then leverage with algorithms. And the interesting thing is that you get these assumptions result in primal dual sparsity only with carefully chosen loss functions. Or you can start with the loss functions and see for what assumptions would you get primal and dual sparsity. And so long as you get the primal and dual sparsity, you can actually apply our suite of methods for that. Okay, thank you.
Any questions? Yep.
So I have a question about the MCL sparsity.
Mm-hmm.
When you talk about lasso or good lasso, in biomedical domain in particular, there are a lot of applications, right? So you can say for the number of 7 microbes in C. Now, what is kind of the natural, equivalent of MCL sparsity, perhaps in the biomedical domain, in your opinion, right? So is there interpretation which may help us to understand that?
Yeah, so yeah, in one way to think about, I guess, the MCL sparsity is that imagine it's actually a doctor, right? And then, or a resident, let's say, because imagining doctor is an expert already. So for the resident, given a particular case, there is a, imagine it's in the multi-class setting, so that there is a ground truth label for a ground truth disease associated with that case. But imagine that the doctor, the resident, is going to label this case with some other disease, right? And so imagine that they actually think it's not just one other disease, but they think it's one of 10 other possible diseases, all of which are wrong. So those would be the most confusing labels for that resident. Does that make sense? For that particular case.
And so you would be searching for them. I mean, why would you regularize for that?
So how would you enforce this? So that was really our work, which was that you don't need to explicitly worry about regularizing for that. That, if you use the margin loss, would automatically result in primal and dual sparsity. So that's really the advantage of our theoretical analysis, which is that it's difficult to even think about how to enforce that sparsity. So I'm with you on that. But what our theory tells us is that you don't need to think about it. So if you use the margin loss, you can just use your familiar and comfortable L1 regularization, and that would give you that MCL sparsity. Or rather, the MCL sparsity would entail that as well. So.
Okay, let's thank our speaker.
Sure.